Hi, welcome back. So in the previous video, we explored how a Eyebolt from McMaster-Carr uh, is affected by pulling straight up like it's designed for, and then also pulling at the 45-degree angle, which is the maximum like allowable offset angle from vertical. And I figured that in this video, we would expand on that. So in the previous video, we simulated an eyebolt and it's physically connected to the ground rigidly. And then we were pulling up here, pulling over to the side, things like that. And there are a few things that this doesn't take into account. So when you have an eyebolt like this, right, typically it's bolted into something. It's not just like attached to nothing. So it's bolted into something, right? And it's got this thread here. And these threads have a preload force that's pulling the entire eyebolt into the material. And what we didn't simulate was the material here flexing and kind of bending down as the eyebolt gets pulled into it. And that potentially could help with some of the forces that we were seeing, particularly in this kind of bottom section down here. So I figured today we would expand our search into this Eyebolt kind of simulation and expand it out to contain the plate below and also the preload. And we'd see if that makes any difference to our overall findings. I expect that it doesn't, but I think this is a good exercise. But the reason that I think that it won't affect much is because none of the effects that we're seeing are kind of in this area down here that is being affected by our changes. So I think what we would see is potentially a reduction in force in this area. Maybe it ends up more in compression and less in tension. But overall, this concerning area up here, kind of where the eye bolt goes from being straight up to being the circular thing, I don't think we're going to see all that much change there. But I think this is an interesting topic, so we'll move forward with it. Now I'm going to start by making a new file, and then I'm going to come over to the Eyebolt file from last time, and I'm going to link the slice here once I find the link button. Here we go. And I'll just drag it over to the other file. So then now we have two parts, I guess. I'm not sure what the second part is. Let's see. If we delete one of the two of them, nothing seems to change. So that should be okay. I'm going to turn the opacity off on this part. There we go. And then I'm going to do a couple of things. So first thing I'm going to do is switch over to part design, and we're going to model this plate area that this is going to be bolted into. And actually, I think I will model this not as a square, but as a circle. And then I'll have maybe 1.5 diameters on each side so that the plate has some flex to it. And this plate thickness is going to be pretty thick. I'm not quite sure. I'll just eyeball it and we'll see if it looks good in the simulation. But that is the plan. So I'm going to make a new sketch here, and I'm going to cut away, and we'll make two circles. So I'm not going to simulate, I'm not going to put material where the kind of eyebolt shaft would go. So let's get rid of the cut away, and I'm going to grab the outside of the eye bolt. Let's see if I can grab that. It does not like me grabbing that, so maybe we won't grab that. Let's see. Does it like me grabbing any of this? It does not like me grabbing any of it. So I guess we won't be doing that today. We'll just be eyeballing it. But I believe that this here, we go back to a page we had from before. This is the quarter 20, so it's 1/4 inch in diameter for the thread size. And the McMaster car without thread is modeled such that it's the maximum thread. I guess the diameter is modeled as the major diameter of the thread, so the threads would be like cut into this part if it had threads. So we will grab this, give it a diameter, and the diameter we'll say is like 1/4, and then, oops, we need 1/4 inch. That was 1/4 millimeter. So 1/4 inch, and then we'll add just like a little bit of it so that it's not on top of the eye bolt. Let's see if I can grab this. Okay, so we'll add, I don't know, a 0.5 millimeters. So that should be enough to get it off of the eye bolt. And then for this one here, we are going to, let's see if McMaster has dimensions for the width of that. So they say that is 0.563 inches wide. So we come over here, and I want the diameter to be the 0.563 inches times, actually we can, we'll check and make sure that looks about right. And yeah, that looks about right. So come over here and grab this. And if you recall, I need another, let's see, I need another 4 diameters. Did that do anything? That did not do anything. So let's grab it again. And we need times 4. Oops, maybe it's because I put it on the right side of the number. So times 4. And the reason I chose 4 there is so that I have 1 diameter in the middle, and then 1 on each side, and then an extra half diameter past that. So I think that's going to give us enough area to properly model the plate without having the boundary conditions affect too much. So then I'll pad this, and let's pad it, I don't know, let's say 35. I just want it, oh, that's pretty thick, maybe not that thick. How about 20? I want it thick enough that the boundary conditions don't affect the rest of the plate. But since I'm not planning on pinning the bottom surface here, I want it thick enough that it's not going to like bow down too much in the middle. So, because that wouldn't be a great simulation either. But looks like we're doing good here. So I'll grab the measuring tool because I need to move this down to where it actually is supposed to go. We'll measure the distance between these two, and 23.81 millimeters is the distance we need to move it. So come over here to body, placement, position, and I need to move it in the Z direction down here in the right hand corner. You can see that, or the Y direction. So we come over here to the Y direction, we need minus 23.81, and those two should be exactly lined up now. They look pretty good. And the reason I am not offsetting this down, so there's a little bit of gap in the middle, like I did with the inside kind of eye bolt part of it, is because I'm pretty convinced that because of the preload, these two surfaces are going to end up in contact. So I'm pretty sure that the scenario where the eyebolt is like this and the surface is like this, and this area here is not in contact, is not going to happen. So I feel pretty confident that we can just bind these two surfaces together using the meshing tool, just by putting them on top of one another. Instead of doing this type of thing where then we'd have to use the contact tool, and that adds a lot of complexity to solving it. So it makes your mesh, you know, more difficult to solve. There's more constraints required. It's more difficult to converge. So it's just a big hassle, and I want to avoid big hassles at all costs. So, but I think we're looking good here. So I'm going to switch over to the FEM workbench and then get an analysis block and a material block. And if you recall, let's see, if you recall here, I believe this part is steel. Yep, it says right there, it is steel. So should be good to just grab steel generic. Let's see, where is steel generic? Here it is. Okay, so both these parts are steel generic. I think that's okay, since this plate here, or I guess this eyebolt obviously is steel, but then the plate, is not super important for the simulation because it's so thick. It wouldn't really matter what material it is as long as it's got some amount of stiffness. So we've got that. We need some boundary conditions here. So grab the fixed boundary condition, and I'm going to fix the outside of this. And let's see, grab the force boundary condition. We will grab these two faces here. Oops. And then for the direction, I need to come over here and I need to grab the sketch with the direction in it. I believe it is this one. So come over, grab the link tool, and we will drag that one onto this other project also. Once again, it's imported two bodies. So I guess we will leave it at that. Let's see. Open up the analysis and the constraint for the force. We will select a direction. Let us see. Direction does not like it. My guess is it's something to do with this second sketch. Let's delete that one and we will base it off the original. And select that. Direction, yes, that was our issue. Okay. And then, of course, we need the preload force. So I'm going to look up the preload for a quarter 20 clamping force. Is a similar thing to preload. And let's see, these guys say quarter 20 clamping force is approximately 500 pounds. So let us move forward with that assumption. Sorry that took so long. I probably should have prepared that. And let us see. Grab the force constraint over here and grab the surfaces on the bottom. The direction can be this one, but in the other way. Okay, and the force in newtons, so we need pounds to newtons. Let's see, pounds to newtons, and 500. which is 2224 newtons. So 2224 newtons. Okay, and if you recall back to our McMaster car bolt, the vertical capacity is also 500 pounds. So that is 2224 newtons also. So we will put 2224 newtons in the vertical direction. Alrighty. And lastly, all we have to do is mesh our system. Oops, I've actually forgotten to combine these two things together. So we'll do that quickly. Come over here to Part and Boolean Fragments to merge the two shapes together. And let us see, we probably have to go through and fix our constraints. So this one here, okay, the force constraint, remove that, remove this, select those two faces again, add them back, and for this one we will remove both faces, and then come down here, and add those back. Alrighty, and now we should be good to mesh it. So switch back over to FEM and mesh, and we'll see what it spits out to begin with. Before, as I recall, it was a decent mesh, so hoping that this one is also decent. Seems like it's taking a bit longer than one would hope, so it's possible that this is going to have some type of issue. It's quite concerning, but I guess we'll let it think, and we'll come back when it's done. Okay, so let's see, it is finished here. Looks like it's decided that it needed a pretty tight mesh around that corner. So we'll click OK on that. And I just want to take a quick look at this mesh before we get too far along here. So hiding the Boolean fragments. And let's change the appearance of this mesh and give it a little bit of transparency so that we can see through to the other side. Okay. And it is quite slow. But I believe it did what we're looking for. I'm looking at it, it looks like it's just a very tight mesh around this area here, which is not quite what we were looking for. I might change the minimum element size to get rid of this like madness, because this is going to take like a million years to solve. So that is no good. So get rid of this mesh and try again. Alrighty, so it looks like it finished deleting itself there. So we can come in and get a new mesh, and let's see. I am surprised that there is no like minimum element size box. So I suppose we want to have a very coarse mesh, or maybe user defined, and let us see. It's possible that we go in here and we just delete these two faces and call it good, because those two faces seem to be where the issue comes from. But I guess we will see. We will see. It's also possible that these two faces are a bit too close together. So that's another area of concern. But overall, I am unsure. So what do we want to do? What do we want to do? Let's try and get rid of these two curved faces here, because those are, I think, causing us issues. So I'm going to come over to, let's see, there is a defeaturing tool here, I believe. So we will try it out. I believe it is this one, remove feature from shape. So I've had luck with this in the past. We'll see if it works here. It's not seemed to have worked. You can try that again. Okay. Well, let's move over to the defeaturing workbench. This, I believe, is a workbench that you install separately. Oops, it is disappeared. Okay. I obviously don't use this very often, so well, let's get rid of it and let's bring these back over to the side. Okay. Bring the workbench back. Okay. So this face, and I want to remove faces. That one, I don't know. Well, let us give up on defeaturing that part. It's possible that because it's imported geometry, it doesn't work quite the same as if it were created in FreeCAD. This might have been brought in some kind of funky surface. So switching back over to FEM, let's see. What shall we do? What shall we do? Let's come over here and let's grab a user-defined and segments per radius. Let us see. Segments per edge, growth rate. Let's mesh it with a very coarse mesh, and we'll see if that changes anything. It's possible that we have to go back and modify this geometry to be easier to mesh. And it's unfortunate the FreeCAD meshing stuff, or at least the FreeCAD meshing that I'm seeing here, doesn't have too many options for forcing the mesher to mesh in like a certain way. Like preferably, you know, I'd like the mesher to, you know, maybe do like 30 nodes around the outside here, and then also like 30 nodes around the big outside there, such that, you know, this is kind of a bunch of beams, you might say. I think that would be pretty standard. But I didn't see any options like that. Maybe they exist and I just missed them. But I think that is the optimal way to do this. I expect this one also spits out a mesh that's pretty crazy. Let's see. It's less crazy than before, but it still seems to be pretty fine around that contact area, and maybe that's okay. Maybe that's what we want. You know, I'm not sure. But let's take a look. So seems like it's pretty fine, especially around the contact area. Um, we might do something funky like move these two parts into one another, and that'll get rid of this odd contact surface. So I think let's go ahead and do that. So that will require, let's see, redoing our Boolean fragments here. So I will go ahead and delete that. Get us back our two separate bodies. And then I'm going to grab this body and we'll move it up like maybe 1 millimeter. Okay. So moved up 1 millimeter, and we can, I'm also going to go in here to this body and edit this sketch and make this inner diameter slightly bigger. That might also help with our issues. Okay, so if we look down here, we can see there's a much larger gap, but that gap shouldn't make all that much of a difference. So then I'm going to switch over to part, grab the two shapes, and Boolean combine them. Okay. So now that I've got this fusion shape here, which is kind of similar to what we were doing before, except this is, instead of two shapes in the same body, it's one shape now. So this mesher shouldn't have any issues with this, I believe, but we can check that here real fast. So FEM, the meshing tool, apply, and I guess fingers crossed, oh, so much faster, so much faster. Let's see. It is an okay mesh. I might change the maximum size to be slightly smaller, maybe 10 or so. I believe that this section out here, oops. Let's see, I believe that this section out here is too large, so maybe we take it down to 5. I'd prefer to have kind of an even spacing of nodes, maybe even smaller than that. Let's go like 3. Okay, that looks pretty good. Let's come down here and take a look at this. That looks pretty good. This is all looking pretty fantastic. Okay, so then we grab the constraints, except we need a shape that we can actually select for the constraints. So add a constraint. This is the fixed constraint on the outer surface, and then a force constraint on these two surfaces. Okay, and the second force constraint on the bottom surface. Okay, and then I believe that is everything, so we should be good to run this. And since we fixed the issue with the, I guess, very, very, very intense mesh we had earlier, I don't think this is going to be a super crazy long simulation. If we were simulating contact, that would probably be a completely different story. This would probably take forever because you'd be simulating on those very fine meshes, and you'd be simulating contact, which is very, very difficult. It takes a lot more steps to simulate. But let's take a look at the results. So look at the displacement here. We can see that this part is moving up and the rest of this is basically not moving at all. Take a look at stresses. Looks like our maximum stress is pretty large and the rest of this is not super big. It appears the maximum stress once again is in the corner there. So that's about what we would expect. That's kind of a concentrated stress caused by the energy flowing around the edge of that fillet. But that's okay because the bulk material here, as long as it's not all yielding, would be able to take that up. We can look at the histogram and we can see that the majority of this material, I believe 250 is where we considered it yielding before. The majority of the material is not yielding. So we can come over here, grab a deeper analysis into this. I will copy these results so that they're separate from the results that we had before and add in a analysis pipeline. And then in this pipeline, we will grab the clip filter once again. We will clip based on von Mises and at 250, which is the yield point. Alrighty. And let's see. Oops, outline, we want surface with edges. And for field, von Mises vector is okay. Alrighty, and as we can see, it looks very similar to before. We've got these two areas up here. And those are caused by our force, so they're kind of fake areas. It's just because our force is concentrated in that particular section. And then we've got these kind of very thin surface ones, but those are okay because the bulk material will handle the rest of the load. So no risk there. This section here is okay for the same reason. The bulk material will grab the rest of it. And then these fillets here are just stress concentrations. So those are okay, because I guess once again, the bulk material here is not yielding. So there's not too much of a concern there. Overall, very, very similar to what we were looking at before. And let us see if we grab this, hide the pipeline and the other results. And I want to change the force here. And let us see, I need one more thing, this sketch here. And the constraint force, we will delete these two, add here and here. And then we will change the direction of it to this one. And it looks like it's going in the wrong direction. Actually, I might have grabbed the wrong force here. I guess we will see. What is this one? Oops, yep, I did grab the wrong force. So let's come back here and we will put this one back on the bottom. And we'll set the direction back to what it was before. And I believe it was reversed, so it's pointing down. Okay. And then the constraint force here, which is the one we should have actually been changing, we will change. Grab those two. And this direction here. Alrighty. And then I believe that is it. So we will rerun the solver. And I believe what we'll see here is that the constraints that we did on just the eye section, the eye part of it, were good enough to simulate the rest of the material. I guess good enough to simulate for this particular setup. And the rest of the material is so strong that it runs no risk of yielding. And in fact, that this is probably very similar to the one we ran before, because the force going up here and the force going down here cancel each other out. So this pinning force from the side is probably not actually contributing much. But I guess we will see. So taking a look at the results here, von Mises, we can see that they're quite high once again. And once again, it looks like our highest spot is the fillet here, as would be expected. Take a look at the histogram. So 250, get quite a few bits here that are yielding, but still, most of it is not yielding. So we're going to have to take a further look to determine whether this is okay or not. So I'll set up a results pipeline, and in the results pipeline, grab myself a scaler, von Mises clipping at 250, the mode surface with edges field von Mises. Okay, and let's see, it's looking quite similar to before. It appears that in this particular setup, we're not getting quite as much stresses down here as we were before. Let me see if I can go grab the results that we were looking at before. So let's see, which one would it be? Would it be this one? Too many questions, too many questions. Let's see, which one of these is doing things? So it appears this one, I believe, is the bending or the pulling from the side. You can tell because this is over to the side here. And this one here is, let's see, appears to be pulling from the top, but I believe this is the one where we increased the factor. So let's put that back to 250 so we can get a accurate comparison. Oops. Well, it looks like it disappeared on us. So we'll just compare this horizontal, or I guess 45-degree version. But from right here, I can see that they look almost identical. So we switch over to this one. You can see that we've got this same kind of feature on the top here, where it's got this divot in it. And then you've got this, kind of same yielding cave formation here, where on the other side there's kind of like a slot. So overall, very, very similar, very, very similar. See if I can flip back and forth between the two of them. It is, I guess it's possible I could copy this one here over into the other file. So we'll see if I can do that. Oh, there we go. So you see these two are basically identical. Very, very, very similar. A few kind of odd things here, but those are, I guess, outliers probably with the mesh. Overall, almost identical results. So we can see that simulating the rest of this material down here does not change much, which means that this material and the plate that it's bolted to and the preload here do not contribute. Well, I guess the preload contributes, but that's because we kind of simulated it before, and I'll explain why. But like the plate and this kind of skirt thing don't contribute a lot to the kind of resistance to yielding in our simulation, because all of this stuff is kind of up here in the difference. Although it is possible that if you were to use an I-beam without the shoulder, without the skirt bit, that it would yield kind of all the way down here. And you would have to simulate that again. So I'm not saying that this skirt is not doing anything. What I'm saying is that the skirt in our simulation is not contributing to the area that is of interest. So we don't have to worry about simulating it with as much precision as we would if it did actually, I guess, contain the area of interest. And before, if you recall, we had pinned this thing to the ground here, and that actually kind of like halfway simulates preload. So it doesn't simulate the skirt being pinned, I guess, being pulled down. But what it does simulate is the entire like bolt part be pulled down, because it's the reaction force for our pulling up. So it should be approximately the same for this up direction. And then for the horizontal direction, it's probably almost the same, because the force comes down like this, and this is going to end up with some type of force on it. Difficult to know, but it's probably about the same, so I wouldn't worry about it. But from this, I guess you can learn that you don't need to simulate the entirety of your model. You only need to simulate the section of interest here, and then the rest of it you just need to get good enough, such that it transfers over to the section of interest in a good way. And I guess the important part here is knowing what section particular bit is actually of interest. So I hope this is interesting, and I hope you learned something from it. Um, I certainly had a interesting time learning lots about the meshing. Um, but yeah, so I hope you have a nice day, and I'll cut it off here.